Welcome to Breadboarding. This is video 37 in the Breadboard 8088 PC series, and in this video we're going to be looking at a diagnostic ROM. So as part of our plan to build a breadboard PC, we've managed to get PC DOS 2.11 running, but some of the later versions of DOS are still not running correctly, and there's some problems with the DMA and floppy disk controller, which I've been looking into. I had a suggestion from Dave about using the Ruud Diagnostic ROM. Now, the Diagnostic ROM is for IBM PC, PCXT compatibles. It originally was written by Ruud, Boltison up to version 3, and from version 3 onwards then Modem 7 or Ray at the Vintage Computer Federation forums and -0degrees.net has actually taken that on and extended it. What it does basically is replaces the BIOS/monitor ROM and does diagnostic testing. It works with monochrome display adapter and CGA video cards, so we have an MDA card, and it actually uses part of the video RAM for stack, so it isn't actually dependent on the main dynamic RAM, DRAM or system RAM. And the breadboard PC though does differ from the original PCXT in a number of ways, similar to Sergei Kislev's XI8088, so we'll just have a quick look at that now. So we're trying to run PC DOS 2.10, 2.11, that works okay, but later versions of DOS don't. The video is monochrome display adapter compatible, however some of the timing is actually been updated for VGA output, so it'll actually work with modern video equipment. And there's also a VGA palette and digital analog converter that needs to be initialized. We are using static RAM, but that does mean that some of the tests in the diagnostic ROM are testing out dynamic RAM in particular, and also some other things to do with the parallel port and speaker are slightly different. We also have dual interrupt controllers for the breadboard PC, so we're able to add a mouse and network card in later stages, and also we're using a PS2 keyboard mouse controller and also 3.5-inch floppy disks rather than the older 5.25-inch ones. So this means that we do need to make some changes to the diagnostic ROM code. So if we take a look at the site, so -0degrees, I've referenced a number of times before, is a really good site, so thanks to Ray for making all this available to us all. And if we go down towards the bottom, we can see that there's Ruud's Diagnostic ROM. This for originally, I think it was 2010 when Ruud's Diagnostic ROM was originally published online. And there's a lot of background information about here. The main thing really is if we've got an MDA card and we also have a power on self-test port on port 80, then we can actually get all the diagnostic information. And so I've spent a number of days updating the ROM code to actually work with the breadboard PC. And there are some limitations, and there's quite a lot of detailed documentation here, in particular around the test descriptions. So if we actually go into version 5, the most recent version, and you can see there's a lot of detailed information about all the tests, what is actually going on here. And to cut a long story short, I've gone through all this sort of stuff and updated it where all the differences and things are. And what it does is actually outputs a number of codes. And if we look at the documentation here, we can actually look at the checkpoint codes. Again, I think it takes us back to the same information. You can see these various checkpoint codes. So 33 is used as a test to the post port. And then there's all the other various checkpoints all the way along here. So when we actually see some of the numbers appearing either in the power on self-test logs or on screen, then this is where we can actually cross-reference them. So if you download the code here, what we actually get when you download it is a zip file, and in the zip file you've got the assembled binary and also the source code there. And if we have a look at WinMerge, and I'll go through the differences that we've actually done here. So this is comparing version 5 with the version I've created. So I've basically called this sort of one version 6 for breadboard PC. So this has got all of the changes necessary for the MDA video card we created with the VGA compatible output, and also has got a few other fixes and things, and basically commenting out stuff that's not relevant for the breadboard PC. So just going to quickly go through this. So we've got the NASM assembler command line there. We needed to add a second programmable interrupt controller, so that's the second pick. And then I have modified, there's a couple of macros which are used to log the output to the power on self-test port, COM port, LPT port. Now I've commented out all the LPT COM port stuff because we're not using that, but it will still actually output down to the power and self-test port, which is on port 80, you can see there. Then we get down to the check. So you can see here, this is actually starting with checkpoint 0. Now, there were a couple of bugs in here. I did find that some of the clear screen was actually updating the screen twice as much as it needed to do. So it originally had here 4,000 words, which is actually 8,000 bytes, and in fact it should be 2,000 words. So I have corrected that, and when I was looking at this with the logic analyzer, I just saw that it was actually writing to twice as much video RAM. That's a minor correction, and I think that was both in the MDA and the CGA code. Now we've also, once we've actually got sufficient test going on here, which actually test the video RAM and made sure that the unused area of video RAM, so there's about 96 bytes at the top of the MDA address space, which are not used by the video card. And so tests here use that for the stack. And once we've got a stack, we can actually call the standard Breadboard PC init palette routine, which I've got from the main BIOS. And then where we're disabling things, I've jumped around things like doing checksums and things like that. Just don't want to checksum the ROM at this point in time whilst it's still actively being developed, and outputs the checksum. If there is a checksum failure, it will output the checksum value. Where I have skipped the tests, you'll see when we run this that rather than the passed or fail, we just get skipped on screen. There are a few areas where I've changed the no ops to do the jump short, which apparently is the preferred way that the BIOS does for providing a short delay. And again, there's various tests, particularly to do with the dynamic RAM and parity. So there's no parity with the Breadboard PC. So we're disabling the parity tests. And also we have static RAM, so we don't need to worry about some of the refresh timing tests. So the dynamic RAM refresh and slow refresh we're skipping. Now this area is where I've modified the code to do the 2 interrupt controllers, because this was actually causing it not to work properly without having the chained interrupt controllers here. Then what I've also done is I've taken in Sergei Kiselev's BIOS code for the PS2 keyboard initialization. So this XT code has the original keyboard interface, which uses the parallel port. So I've replaced this with the keyboard controller in it, and a large number of the tests and things which are further below here are now actually disabled. And in fact, it based just the initialization and then really doesn't do any further reading and stuff. Not really had any problems with the keyboard. It's really the DMA and the floppy disk controller that I'm more interested in. So on the DMA side of things, I have made a few corrections that I was getting failures in the DMA sometimes. So I've tried to do some of the other changes that I've done on the main BIOS, in particular disabling the channel 2 whilst it's being configured and adding a few more of these delays between updating the registers. And then when we get to the floppy disk drive, there are 1 or 2 change in parameters. The default parameters in the Diagnostic ROM are 5¼ inch drives, which obviously the default for the original XT. I've updated that for the 3.5 inch values. And then we skip over some of the stuff to do with the switch settings, because we don't need that because we don't use the switches. And then this is a version of a routine where we're just doing the skip message as a pass or fail. And then we've commented out the output to the parallel ports. And then the RAM testing, we ignore the parity since we don't use parity on the Breadboard PC. Then this is the reset routine, which has been switched to use the PS2 compatible routines for that. Then more stuff to do with disabling the parity checking, making sure that the 0 flag is set for the parity checks. And then this is where we've got the different timing signals. So the original MDA card only worked with MDA compatible monitors, which were about 50 Hz refresh rate. So this actually updates the video controller CRTC chip to actually use VGA compatible timings. Just our text titles, our skipped message, and then this is the additional code I needed to add for defining the VGA palette register definitions. In order to run this, it also needed to include a couple of the other routines, particularly for the keyboard controller, needed the error numbers, the delay, and these other additional items. So these were basically to get the BIOS code to assemble cleanly within here. And then there is a checksum there. At the moment, the checksum checking is disabled, but once this is finalized, we can update the checksum so that all the checksum checking works okay. So after that's been updated, all we then have to do is to go into the command prompt, or just assemble that. And then if we actually go to put the BIOS ROM into the EPROM programmer, we'll just now write the diagnostic ROM to a a spare one that I've got here. So always recommend you read the chip that you're going to try and program in case you've put the pins in incorrectly. So that's read okay. It's all FFF. Now when we load this, what we actually have to do is to make sure we load it into the top 8K of ROM. Now this is the 32K ROM, so we actually need to be careful when we're loading this. So all I'm doing here is selecting the binary file that we've just assembled. Now what we have to do is to locate this at 6000, and we also want to clear the buffer with zeros. So this just means that when the ROM check code runs, that it does a checksum, and if it sums to 0 then it will count as a success. So by clearing the lower areas of the ROM to 0, then it'll mean it'll actually pass the checksum test. Okay, so we'll just program that. Okay, so we'll put that back in the breadboard PC. So just take the ROM out of there and put it in where the BIOS normally goes. Okay, so before we can run this, what we just need to do is to set off the logic analyzer running, so we're actually recording the power on self-test port. So this is on the power on self-test port, is actually triggered on the reset line, and then we should actually get all the post codes coming down here. So I'm just going to record this. So I'm just going to power this on. It will make a bit of a beep before it actually updates the screen, and then once it's done the updating of the screen, we should start to get the video output. So move this to full screen. On the top right hand corner you can see the code of the test currently running. Now we'll speed this up because the RAM testing will take a little while to go all the way through. So you can see here there's a couple of tests here. The refresh and slow refresh tests have been skipped, and then we've got various interrupt tests. Trying to read the floppy disk drive, so you might just hear the floppy disk access. And then you can then see that there are some of the ROMs we've not actually got anything installed here, but the F800 is the top 32K, and you can see that these other ROM areas are actually passed because they're all zeros. You can see that now the test is actually repeating itself, so it completed one pass, and this will just keep looping around until such time as it finds a critical failure. Now what I will try and do is to record when I get a DMA controller failure, and I'll then try and do some detailed logic analyzer analysis for that, because occasionally this does actually fail on the DMA controller, and I suspect that is the reason why I sometimes get problems loading the later versions of DOS that need to read more off the disk. It appears that the DMA controller has a fault towards the later parts of loading the MS-DOS 3, 4 and 5 operating systems. So this appears to be working. We've got the keyboard tests are working, the floppy disk controller tests appear to be working, although when I have actually looked at the logic analyzer diagnostic output, it does appear that not all of the DMA related signals appear to be working properly there, so I'm going to have to look into that. But it's certainly given a good sort of stability test. It will certainly test the RAM very thoroughly, and if you had dynamic RAM, where I think the older PCs tend to have flaky DRAM modules, then this will certainly probably help to shake out any problems in that area. So what I will just do is to leave this running for another sort of number of passes to see if we get any critical errors. So we'll speed that up and we'll come back once we've tested at least sort of 10 passes. Okay, so after 7 passes, the DMA controller has failed. So this obviously indicates there is a problem to do with the DMA controller somehow. So what I'm going to do is to go away and have a look and see if I can reproduce this failure whilst running the logic analyzer on it to actually see if we can get anywhere. Now this is just showing the logic analyzer output, and what we've got here is our initial 3.3 code here, which was the test code that was output. Then we can see all the way down here we've got 0, 2. It's not always sequential in that there are gaps sometimes in here, but we can sort of see going all the way down through the tests. And this is the same as the code that appears in the top right hand corner of the screen during each of the tests. And you can see it gets all the way back to the end here to 7.4 and then starts back round again. Now if I had actually been logging this when the DMA controller test failed, then it would have actually output a different code for the failure here. What I'm going to do is to put the other logic analyzer on this and actually run these tests until such time as I get the DMA controller failure. Let's take a look at the logic analyzer traces that have come from this type of situation. I have run the logic analyzer a number of times to reproduce this issue, so it may not be the identical problem, but it should actually give us an idea of what's going on. So here we have the outputs from our 32-way logic analyzer. So we've got all the address lines going down to A15, then we've got the D0 to D7, got the top couple of address lines. Now we don't decode A16 because that's not normally needed and we don't have enough lines otherwise. Then we've got the read and write for IO and the read and write for the memory, and then I've also got the DMA chip selector. What we're going to look at first of all is what's actually going on here. So what we need to look at first of all is when do we output code. So we actually output to port 80, that's the power on self-test port 1F. So what is 1F? Well, if we actually go to the source code here, we can see that the checkpoint 1F is actually the DMA controller. So that's actually what's going on there. Now, in actual fact, when we output the text, there is actually an intertest delay, which is about half a second or so. So that's why there'll be a big gap. And then it goes off to do the tests of putting various values and things in the registers, and then if it fails we actually get 9F output to the power on self-test port. So that's when we output the test start. You can see here there's quite a gap, so that's almost like about 494 milliseconds. Then if we actually drill down to the end here, these IO writes are where the code is actually writing to the DMA controller. And in fact, the test at where this actually fails is this one here. So this is actually the last test before it goes to the failure code. And what we can see here is it's reading 000 and it's getting BF back. Now, if we just go back a little bit earlier, so this is the 0000, 4 zeros. And what's the value that we actually wrote to that last? And if we go back here, we should be able to see that, there we go, 0 we actually wrote, so IO write there, FFF, and there'll probably be another write as well. So this is the lower, least significant bit and most significant bit. They've both been written as FF. Then, in fact, then they've been written as 0 and 0. So as part of this test, set them all the registers to FF, then to 0, and now it's reading back 0, and rather than coming out as 0, it's coming back as BF. So something's definitely not right here, and in fact we can see here that there's a bit of time here where it's, you know, something's not quite right. And if we go along to the right here, we can then actually see that port 80 is the power on self-test port. We get 9F being sent out there. So this looks to show us that something's not quite right going on here. And this is just really reading and writing to the registers in the DMA controller. And if we can't read and write to these registers reliably, then the chances of everything else working reliably is remote. So what I'm just going to do now is to have a look at the equivalent functionality when we try and boot MS-DOS 3.3. So what I've done here is this is an extract of where we're trying to boot DOS. And if you see these bits down here, these chunks here are where we're reading 512 bytes off of the floppy disk. And we actually managed to read quite a bit of the operating system. So we're reading the boot sector, the directory entries, the file allocation tables. Then we're reading about 18 sectors. Sorry, with 36 sectors. These are 18 and 18. And the last byte that we actually write to memory here, if we go in here, we can see that the last byte that we write to memory is 54FF. So the next byte we'd expect will be 5500. And in fact, if we go and have a look at where the DMA is being set up, so this is where this blue bit is here. This is where the values for the target address are being written, and you can see that we've got 0055. So this is the least significant byte, most significant byte. So that is definitely being written correctly. Now, this actually fails at this point in time. To the right hand side here, this is where it actually fails, because we can sort of see that this here is what we'd expect for 512 bytes, and when in fact we get to here, we can see that this is a much shorter period of time. In fact, if we drill down here, what we can see here is that the address, rather than being 5500, the address is 0055. Now this is a problem that I had in the early days where the bytes were getting reversed, but this appears to be happening even with the newer intercell DMA controllers. So it's quite likely that it may not likely to be a chip problem, and there may be something with the board. So what I'm going to do, I'm not going to do any further on the video at this point in time, but the Diagnostics ROM basically has helped to highlight where there are some potential problems reading and writing to the DMA controller. We've also been able to see here that we also get these values being reversed. So what I think I'm going to do is to take one of the DMA controller tests that I had that was running standalone, and what I think I'll do is I'll add this into the Diagnostic ROM. And the Diagnostic ROM, as it stands at the moment, is quite clear that really the tests that are being done on the DMA controller are very minimal. And if we go to the test descriptions here, in fact what we'll find, here we go. So what we can see here is the DMA controller does the read and write test of the first 8 registers. Note this is barely testing the 8237A DMA controller, so I think we probably need to have some more tests here. So I'm going to break the video here. So by converting Ruud's Diagnostic ROM for the Breadboard PC, we've actually been able to verify that over many runs everything runs okay, but then very occasionally we do get this DMA controller error. Now the tests which are currently being done by the Diagnostic ROM are fairly limited. So what I'm going to do is I'm going to look at extending those tests and try and see if I can drill down into the problem that may be causing the DMA addresses for getting messed up, and in particular the issue I saw with booting MS-DOS 3.3 where the most significant byte and the least significant byte are getting reversed. So if you don't want to miss out on future videos, please hit subscribe, and if you can hit like, it just helps to make the videos available to a wide number of people. Thanks for watching.